Hello, I am Stéphane Bonnet, working for Thales Corporate Engineering, a Thales unit that defines and deploys engineering practices, processes, and tools. I have been leading the MBSE coaching activity for a few years now. What I am presenting here is the current result of a 15 years journey. None of the things I will talk about have appeared to us suddenly. We have slowly refined our practice and understanding of MBSE over the years. I must credit a few of my colleagues for their contributions to the slide deck. Before diving into the topic of this talk, I am going to start with a fun introduction we typically use in our MBSE awareness-raising sessions and trainings. The complexity of systems never stops increasing. Systems are more connected, software is ubiquitous, industrial schemes create additional interfaces, and so on. There is also more stress on our engineering, as we are facing new competitors and have shorter time to market. Some disciplines have emerged, or at least became more important. Cybersecurity, big data, AI, health and usage monitoring, UX design. But there's one thing, however, that did not really increase over the years. It's the brains of the engineers. At least, I've seen no proof yet that the younger generation of engineers is significantly more capable of the previous ones. So what do we do when we have an increased complexity and the same computing power? We involve more brains. And we ask more to each of these brains. We ask them to do more with more constraints and less time. We also have to cope with very demanding customers. And because there are a lot of new disciplines, we have to interact with more peers who don't necessarily speak the same language. So we end up having communication and information management problem. So what do we do when we have communication problem? We work on the language. We have languages for mathematics. We have a language for construction. The electrician and the plumber all are able to read the same blueprint. We have language for electronics. We have language for software. What about systems engineering? We basically have Excel, Visio, PowerPoint, Word, DOORS. We basically write requirements with natural language. We use ad hoc spreadsheets, a bunch of Visio and PowerPoint diagrams, a pinch of traceability. Back to the INCOSE definition of MBSE from Vision 2020. MBSE is a formalized application of modeling techniques to support system requirements, design, analysis, verification, and validation activities. My talk today is a 360-degree tour of the Thales implementation of MBSE. I will first focus on the conceptual background we base our work on and try to explain how it benefits our engineering practices. I will then spend time explaining how we encourage, implement, and monitor the cultural change. I am not necessarily going to promote Arcadia or Capella, but I need to explain a bit of the foundations on which we base our work. Most of the principles I will describe today could even make sense with another method or another tool. Arcadia is a model-based engineering method. It defines a set of high-level concepts and the associated viewpoints. Capella is an open-source graphical modeling workbench specifically developed to implement the Arcadia method. It provides the notation and diagrams. While this talk is about MBSE, I'm still starting with requirements. It cannot be argued that requirements form the backbone of our current engineering practices. In Arcadia, we complete these requirements with models. A need model helps formalize and consolidate customer and system requirements. A solution model helps understand how the system works, what are the different constituents, what functions do they provide, what are their interfaces, and the solution model helps elicit and justify new requirements for the subsystems. If I wanted to summarize the Arcadia method, I would say that there are two orthogonal dimensions. First, the concepts. We have 5 families of concepts: capabilities, functions, components, interfaces, and behavior. And we have engineering perspectives, covering the need and the solution. 2 perspectives are dedicated to need capture, and 2 are dedicated to the solution description. The 4 engineering perspectives exploit the same concepts for different purposes. The color here is not random, as you will see later in the presentation. Bluish is associated to the need model, pinkish is associated to the solution model. The concepts we use in Arcadia are not rocket science. It all starts with capabilities, which are high-level services provided by the system of interest. Capabilities are described with functional chains and scenarios, which involve functions that are connected with functional exchanges, expressing dependencies between the functions. Functions and functional exchanges are allocated to component and component exchanges. And to further specify what is exchanged between the functions and what has to be in the interfaces between the components, we use exchange items, data, interfaces. Finally, we capture the behavior with modes and states that are defined on components and specify which functions are available or not available in such or such context. Finally, we get the 5 families I was talking about: capability analysis, functional analysis, behavioral description, structural description, and interface description. And we add the textual requirements. All along this talk, I'm going to use a small example of a drone-based system. This drone is actually performing an inspection of the exterior of an aircraft. So we have one capability, which is to visualize live data during the flight. And this capability is described by 5 functional chains, which involve functions that we see on this data flow diagram. The 2 functional chains are highlighted in blue and red. The slide summarizes our conceptual foundations. Note that in many approaches, you don't have all these different engineering perspectives, and you don't have such a clear separation between need and solution models. We now have the conceptual background, but what do we do with all this? How do we use models to leverage our engineering practices? In the landscape of engineering artifacts, we typically have requirements on one side and models on the other side. And between them, we have traceability, like describes, justifies, and so on. As models rely on a precise language, they add rigor by significantly reducing ambiguities. And because they obey strict construction rules, models can be automatically processed and analyzed. Among others, this allows to ensure completeness and consistency. So, if models are more formal and more rigorous than textual requirements, why aren't they considered as requirements themselves? Our major finding to advance our MBSE practice is here. I said previously that requirements are at the center of our engineering activities. I stand by that, but requirement can either be textual short statements, either model elements. Textual and model requirements actually complete each other. A model requirement can formalize a textual requirement and explicit its effects and ramifications. For example, I might have a textual requirement specifying that whenever the user moves the joystick, the flight plan would be interrupted. In the model, we implement that with a transition between 2 modes, and it is pretty easy to compute which functions is going to be available or not when we change mode. So we better understand the consequences of this requirement. Some expectations, for example environmental, regulations, are easier to express with textual descriptions. For example, it would be pretty difficult to express in the model that the system should be operational in windy conditions up to 60 kilometers an hour, for example. And then some expectations on certain model elements at a given engineering level do not require a formal modeling, which is left to the subsystem design. Here, on this data flow, I'm specifying that I want to display some things on the tablet while the drone is flying. But the way the things have to be displayed is not my concern. I am just expressing textual requirements, what we expect, but the design will be done later on by the downstream engineering team. Considering model elements as requirements is a game changer, and I will illustrate that here with 3 happy consequences. It strengthens the articulation between upstream and downstream engineering. It brings a better mastering on V&V. And it is a real enabler for incremental development strategy, and a smoother transition to software. So let's start with the contracts between engineering levels. It all starts with an operational analysis, what the users of the system need to do. And we're going to do an operational analysis model, a system need analysis model, perform a first functional analysis, and try to elicit the textual requirements and the expectations on the system. Then we're going to do the architectural work, identifying the system constituents, specifying how the system works, and identifying the functions that have to be performed by each constituent. And by doing this work, we're going to identify and justify the interfaces between each constituent. The objective is to prepare the contracts for the subsystems and guarantee their proper integration. Based on this system solution level, we can initialize the subsystem need models. The tool is able to compute the context of one given constituent in terms of expected functions, exchanges, interfaces, and so on. And for whatever things we were not able to express with the model, we complete with textual requirements. So the data package the downstream engineering team receives is both a model and a set of textual requirements. And they will later on apply the same approach, working on their own solution level. So this is a zoom on the production of the downstream engineering model. The Capella tool has an add-on that allows to automatically initialize the subsystem need model. So here in the system solution model, we have a tablet that is a constituent of our drone-based system. And in the subsystem, it has become the system of interest. So the takeaway here is that the model-based workflow favors co-engineering over the traditional differentiation between customer requirements and system requirements. We want the downstream engineering stakeholders to be involved in the system solution model. Let's now focus on V&V. Now that some model elements are considered as requirements, the good news is we can align V&V artifacts against the model requirements. Instead of associating test procedures directly to textual requirements, they verify scenarios and functional chains. Each step of a functional chain becomes a step in the test procedure. V&V engineers and system engineers work on a common reference. Similarly, the alignment between V&V campaigns and the system increments becomes straightforward. It is easy to precisely compute the functions, components, interfaces that are necessary for one validation campaign simply by running queries on the model. This example here is a real project in Thales that lasted 2 years, involved about 30 engineers, architects, software architects, V&V practitioners, management, and so on. They had one system level, 8 subsystems. That means 9 engineering data packages to keep synchronized. Data package being a set of requirements, a set of models, a set of defects, a set of documents, and so on. Their need model was characterized by a set of capabilities and functional chains. Each capability and functional chain has been associated with a system release. Functional chains have been used as stories or inspiration to write the test procedures. And from a given system release, they were able to automatically create and configure the validation campaigns in our V&V workbench. One very good benefit from this approach is default detection analysis. On the test bench, when something was wrong, it was pretty straightforward to identify the associated functional chain, the exact step that went wrong, and then they did perform impact analysis on the model and check the consistency with the specification. And here, there were 2 options. Either the model was wrong and it created a specification defect that would later turn into a component evolution request, or the model was right, but the implementation was wrong, and in that case, that was a component defect. And it's the first time in Thales that the people on the test benches, when something went wrong, didn't go see the software. They went to see the model. Last, the incremental development strategy. A system or a product can be fully characterized by the sum of all its capabilities and functional chains. When doing incremental systems development, there is an initial preparation phase in which the high-level functional chains are dispatched in several system increments. The system increments are defined with expected functional content instead of being defined by components. So this is the first step. We define the increments with expected functional chains. Then, during one iteration, the work of the systems engineers is to perform a vertical slice of architectural design across the need and solution models, and to end up with a data package that consists in model elements and textual requirements. And during this iteration, the people from the software or V&V are involved in co-engineering activities so that they can start owning the data package that they will receive at the end of the iteration. In the next iteration, the system architectural design team is going to work on another increment, and the software is going to work on the implementation of the previous data package. The same goes for the V&V team, who will start performing validation. At this stage, you should be familiar with the concepts: functional chains, functions, exchanges, textual requirements. While we have often struggled with the transition between system and software, we believe we have now found a natural workflow. Agile releases are synchronized with system increments. A software epic is created for each functional chain defined at system level. The epic is therefore specified by the functional chain and by the textual requirements associated to this functional chain. Software developers then analyze the epic, clearly understand how it fits in the global picture, and the value it brings to the final system or product. They split the epic in several user stories that are dispatched in several sprints. So we're going to take a small example with the drone. We have three teams: the systems teams, the V&V team, and the software team. The system iteration is 3 months. A software sprint is 3 weeks, meaning that during a system iteration, there are 4 sprints of software. The vision of the high-level capabilities of the product is already known and shared. Functional chains have been dispatched in several system expected increments. So we're now working in iteration N. And one of the functional chains that has to be developed is the manual control of the drone motion. The systems team is going to perform a vertical slice of architectural design. During that time, the software team and the V&V team will be involved through co-engineering and reviews. And the test procedures will actually be written also by the V&V team in the same time as the functional chains are created. During the iteration N+1, while the systems team is going to work on another increment, the software team is going to receive all these epics, refine them in user stories, and dispatch them in different sprints. So for example, they have to work on the graphical user interface, the mode supervision, allowing to switch from the automated to manual mode, on the development of the joystick driver, and so on. The pace of the V&V team is aligned on the software team. And during all this iteration, the V&V team will test the components that are delivered sprint after sprint by the control software team. At the end of iteration N+1, the functional chain manually controls the drone motion is supposed to be fully functional and validated. So I cannot emphasize enough the central role now played by functional chains in our practices. They are the unifying reference, bringing all stakeholders together and making them share a common understanding of what has to be delivered. So you now have a better idea of what some of our projects already implement and what we try to promote. However, getting teams to embrace MBSE is still a daily challenge. I would even say struggle. I will try to give a quick overview of what we do to encourage the cultural change. The first thing I'm going to talk about is how we provide perspectives and help engineers and managers understand what they can get from models. So we have 3 different kinds of purposes for models, and more is not necessarily better. So the first objective is to share. I use a model to improve communication and reduce ambiguities. Models describe and provide a common understanding. Engineering is not necessarily model-driven, but models are known by most stakeholders. Second kind of objective is to secure. We want to analyze and evaluate in order to master the system complexity and drive some engineering activities. Through validation and analysis, models are used to guarantee the quality of the engineering data, consistency, completeness, and so on. Models are part of the engineering baseline, and several engineering activities are directly related to model. For example, the V&V or the transition to software. The last big objective for a model is automation. We want to generate documentation, code, or models. Models enable tool articulation of engineering activities horizontally, for example, to integrate engineering specialties, or vertically for the downstream engineering, like transition to subsystems, hardware, or software. We have identified 11 areas of engineering where models are likely to have an added value. The key is to relate what is expected in each engineering activity to what we can get from models. And we've done the exercise for each engineering activity and each modeling objective. So we have worked on a framework that can give perspectives to managers and practitioners. For each engineering activity, we have identified what the model can bring depending on the targeted objective. This framework helps our coaches and experts conduct their framing sessions in the beginning of projects. This framework can be used to orient and assess modeling activities. As the goal is not to scare people, we have 3 possible levels of details: 10,000 feet assessment, 1,000 feet assessment, 10 feet assessment. The 10,000 feet assessment is particularly useful for the management. It gives an overall idea of the footprint of models in engineering activities. It helps orient the expected improvement on engineering. The 1,000 feet assessments is about the contribution of models to each engineering activity. It helps detect weaknesses and opportunities and helps the definition of improvement plans. The 10 feet detailed assessment is closer to a model review. It helps make sure that the content of the model can actually support the targeted objective. So we provide a toolkit for coaches, managers, and architects to perform their own orientation and assessments. The 10,000 feet is about 20 questions. The 1,000 feet is about 150 questions. So they start by analyzing their context, identifying the relevant activities, they answer the orientation questions, and they get a quick and visual overview of the footprint of MBSE in their practices. They can then define concrete improvement actions and then monitor them over the time. So with the conceptual foundations and the engineering objective framework, we have a pretty good toolbox. But there is still a lot that we can do, that we have to do as an organization to support the deployment of MBSE. There are a few core enablers. We've been lucky enough in Thales to have a constant and renewed commitment from the management. We also have a strong motivation and resilience of a network of highly skilled individuals who work together on a common goal. And finally, we have a sizable mentoring coaching force. There is a lot of demystification required. Here is a few things that we hear on a daily basis. I don't need MBSE. We deliver. And we have been delivering for the last 30 years without MBSE. Visio diagrams do the job. And by the way, they look much nicer. This is too big of a change for an added value that is actually difficult to perceive. So many possible ways to do MBSE that I don't really know where to start. So we have to fight this myth. And delivering is different from being competitive. I have no doubt that a project that doesn't do MBSE has room for improvement. Visio diagrams are not enough. You need more rigor. It's not too big of a change. You can start small, identify a problem and try to solve it. And I really like this sentence from David Long: don't seek the big bang, focus on specifics. Modeling activities have to be managed and monitored. If you try to solve an engineering problem with a model activity, after 1 month, 2 months, you have to assess that this modeling activity is actually contributing to solving the problem. And if it's not, you need to reassess and you need to redefine your modeling strategy. And the last thing is, you're not alone to do that. Like we have a coaching capability, and you should use that to help define strategies. We actually don't use the term MBSE that much in Thales. We use MSBE instead. MSBE stands for Model and Simulation Based Engineering. It applies to systems, to software, to hardware, and so on. We have about 400 members on this community. We try to provide 3 or 4 newsletters per year. We have forums, FAQs, and it is really key to communicate and advertise on the success stories. Once a year, we organize the Capella Users Day with an average of 100 participants. It is a kind of giant tutorial where end users can get help from the development teams. It is also a way to get operational feedback from projects and to have networking at user level. We have different kinds of services that we are able to deliver: awareness raising, strategy definition, implementation guidance, and peer reviews. Awareness raising is typically targeted to managers who don't necessarily know what MBSE is. Strategy definition can be targeted to managers who want to implement an engineering performance plan and want to rely on MBSE for that, or dedicated to one given project who has very concrete objectives, and we can try to help them frame their usage of MBSE. To deliver this coaching, we have a few coaches at corporate level, but it's not enough. We have introduced a concept of network of coaches where people from a specific business entity or business line who is an expert can actually act as a coach for another business line or another business entity. And we have about 30 members in this network of coach, and they work on a common coaching toolbox, for example, the objective framework or sample models that they can use, or they investigate on advanced topics. In Thales in 2019, we've had about 60 operational projects who have benefited from coaching. The average coaching effort that is required for a given project is typically 10 days over the course of 4 or 5 months. So we have a website where you can find learning material, industrial case studies. We have a public forum. We have a YouTube channel in which we have done a lot of webinars and explaining some of the things I mentioned today. And of course, you can freely download Capella. Thank you for watching.